All right, so I thought it might be useful to go over the first exam. I know the solution's posted online, but sometimes it's helpful to have somebody walk through it. So starting with the conceptual questions, in the figure to the right, an intercooler separates two compressor stages. So we're looking right here, and the intercooler is right there. And the intercooler contributes to the overall performance of the system by reducing the compressor work input. So the place that it's going to affect things is going to be between those compressors, of course. Yeah, so it's going to decrease the compressor work. When a regenerator is introduced, and remember, a regenerator will decrease the amount of QN because that regenerator, remember where it's situated. It's situated such that the heat that would have been lost by in the exhaust process, some of that's redirected back into the cycle to sort of preheat that air before he goes into your combustion chamber. And so it's going to reduce the amount of heat that you actually have to add from some external source, right? Fuel, right? Burning fuel. And so it's not really going to affect the net work, it's affecting the QN. And so the answer here is it remains the same. Number 3, we have an internal combustion engine in which air is compressed to a high enough pressure and temperature that combustion occurs when a fuel is injected. And so this is a fuel injection. This is a compression ignition engine, right? So it's the air that's compressed, and then once it is compressed to a high enough temperature and pressure, the fuel is injected, and because it's at such a high temperature, that fuel will combust, and that's how a diesel engine works. Number 4, which analysis will yield more accurate results for a gas power cycle? Well, it's going to be the one that's going to be more annoying, right? Um, so yeah, so cold air analysis, cold air standard analysis, it's convenient, less accurate, it's accurate. Yeah, so in general, if it's more annoying to solve, probably going to be more accurate. The Otto and the diesel cycles differ from each other only in the way that the heat addition process replaces combustion in the actual cycle modeled. And that's true. So from 1 to 2, 2 to 3, 3 to 4, 4 to 1. So if you look at the processes for an Otto and the diesel cycle, these are the same. These are the, oops, I'm sorry. That first one is the same. These, the third and fourth one are the same. But this one is either, if it's an Otto cycle, it's going to be a constant volume QN. And if it is a diesel, and it's going to be a constant pressure QN. Yeah, so the answer here is true. And do keep in mind it's the way that it's modeled, right? We're not talking about the actual auto engine or the gasoline engine and the diesel engine. We're talking about the models that we're using for those systems. All right. So 45 points, problem 6. So this is the problem where people tended to have issues with. So let's walk through the problem statement. We have air passing through the compressor. So we're going from 1 to 2 of a cold air Brayton cycle with reheat and regeneration. So here's our regeneration and here's our reheat. And we're coming in P1, 1 bar, T1, 280 Kelvin. And then we've got a volumetric flow rate, V dot 1, of 7 meters cubed per second. Pressure ratio, P2 over P1, is 4. The isentropic efficiency of our compressor is 92%, so 0.92. And the isentropic efficiency of the first turbine, so this guy, is 100%. The isentropic efficiency of the second turbine is 90%. The regenerator effectiveness is 90%. And the temperature of the air entering each turbine, so going into each turbine, would be at T4 and T6. So that guy is 600 Kelvin. And it tells us the pressure ratios across each turbine are equal. So what we're saying is that, let's put it as P5 over P4. So outlet over inlet, is the same as P7 over P6 outlet over inlet for the second turbine. And what we want to find is we want to find the pressure ratios, all the unknown temperatures, the thermal efficiency of the cycle. Yeah. So as far as our assumptions go, steady state, changes in kinetic, changes in potential energy are equal to 0. I'll say old air standard, K is equal to 1.4, and be done with it. Okay. All right. So we know P2 over P1, and we need to find P5 over P4. All we know is that P5 over P4 and P7 over P6, that pressure ratio is equal. So what we need to do is we need to like kind of look through where all the pressures are equal. So we know that across the heat exchangers, P2, P3, P4, all those are equal. P5, 6, those are equal. And then kind of coming out of the second turbine, so P7 and P8. And keep in mind that, yeah, it's not drawn, but this is the exhaust process, and we were modeling that as a heat rejection process. So, maybe I'll actually draw that. This guy is a Q out. This guy is a Q in. This guy is also a Q in. This is our regenerate, or not regeneration, but reheating. So workout. There's a workout. There's a work in. Okay. All right. So P7, P8, and across that last heat exchanger to the left, P1 is the same. All right, so what I need to do is relate the ratios. So P2 over P1. All right, well, I know P2 and P4 are the same, so maybe that would be a good thing to start with. And then P1 and P8, or P1 and P7 are the same. That will be helpful. And then I also know that, let's see, P5, so what we're going to do, I need things in terms of P5 over P4. So what I'm going to do is I'm going to say this is the same as P4 over P5, 5 over P7. So I haven't really changed anything, but where this is going to help me is I know that P5 over P6, or P5 and P6 are the same. So I'm going to put this as, I'm going to keep P5 over P4, but I'm going to rewrite P5 over P7 as P5 over P6. And then I also know these two things are exactly the same. So I could just rewrite this as, oops, and I'm seeing what I did there, I'm sorry. There. I could rewrite this as, did I do this? Oh, I'm sorry. Did I do this wrong? I'm sorry. P4 over P7, P5, P5, 4, 5, 5. Ah, P5 and P6 are the same. There we go. Okay, sorry about that. All right, so let's walk through it one more time because I was going a little too fast. All right, so I got P2 over P1. I'm defining that because I know what that is. And I know that's got, oops, I know because where the pressures are equal to, I know P2 and P4 are the same, 2 and P4. And then I know that P1 and P7 are the same. P1 and P7 are the same. All right. And then I'm just going to rewrite that. So this is P4 over P7, right? And I'm just rewriting it in terms of P4 over P5 because that's what I'm asked to find. I'm asked to find P5 over P4, so need to get that ratio. And then I'm going to keep this guy. That one doesn't change, but and this guy doesn't change, but I am going to say P5 and P6 are the same. Okay, great. All right, so I think we're getting somewhere now. And then I also know that this ratio P5 over P4 is equal to P7 over P6. I've got the inverse of that ratio, but it's the same thing, right? These two fractions are equal to one another. And so I could just rewrite this as P4, P5 squared. Okay. And I know this whole thing is equal to 4. So this is equal to 4 squared. Okay. So P4 over P5, I'm sorry, not P4 squared. Stupid. P4 over P5 is equal to the square root of 4, which is going to be 2. And I don't need P4 over P5. I need P5 over P4. So 5 over P4 is just going to be 1 over 2, or 0.5. All right. Make this just a little bit smaller here. Kind of move him out of the way for now. All right. So we've got the first one. And now we need to get all the unknown temperatures. So I'm going to walk through my cycle. Okay. So I'm sorry, not A. So I've got state 1. Don't need that. That's given to us. 280 Kelvin. And then state 2. And I've got an isentropic efficiency for that compressor, so I'm going to need to figure out state 2s and state 2. So state 2s is going to be found using an isentropic relationship. So T2s over T1 equals P2 over P1 to the K minus 1 over K. All right, and that's a T2s. So T2s ends up being 413, I think, or 16. So 416.9 Kelvin. And then state 2, need to figure out, need to use that isentropic efficiency to relate the state at the end of that isentropic process to the actual process. So, okay, so the ratio of the two works. Ideally, I wouldn't have to put as much work into this guy, so that's going to be the one on the bottom. So I get a CP, T2S minus T1 over CP times T2 minus T1. All right, and so I'm just going to algebraically solve for that. I know T1, I know T2S. So T2 ends up being 427.9. Oh, I think this was just, should have been 1. So 427.9 Kelvin. All right, so as far as, the numbers that I'm going to plug into my governing equations when I get there, this T1 and this T2, okay? And so those are the numbers that you need to find. If you only found T2S and you didn't find T1, probably got docked half credit on that particular temperature. All right, so let's keep on going. Let's go to T3. That a little bit smaller. Okay. All right, so go into state 3. So state 3 is after my regenerator. Don't really know. I can't, I cannot apply an isentropic relationship between 2 and 3. It's not isentropic. So I did see a couple of people doing that. Can't do that. However, what you can do is you can use your regenerator effectiveness equation. So this is going to be Q regen over Q regen max. Okay. So Q regen, if I'm looking at my regenerator here, and I'm looking at this little section here. Okay. Q regen is going into that little section right there. So your equation, it's going to be Q regen is going to be H3 minus H2 or CP delta T, CP times T3 minus T2. And then Q regen max would be if by the time your working fluid got all the way from 2 out to this spot right here, he would have heated all the way up to the maximum temperature that he could have heated up to, and that would be T7. So T7 minus T2. All right, and so I don't really have anything that I can plug in for T7. I need that still, yeah. So I'll need to calculate him, but once I get him, I'll be able to get T3. And if you wrote that equation, you should have gotten full credit. If you didn't, please let me know. Full credit for that particular temperature at least. All right, state 4, I know. Cool. So state 4, T4, 600 degrees or 600 Kelvin. And now we need state 5. Okay. So state 5 is after the end of an isentropic process. So we are looking right here. So it's the end of the isentropic process, so I can apply an isentropic relationship. So it is going to be T5 over T4. I'm sorry. Yeah, T5 over T4 equals P5 over P4 to the K minus 1 over K. K is 1.4, and that pressure ratio is the thing that we just solved for in part A. It's this 0.5. All right, so this guy has to be 0.5. Go. So my T5 ends up being 492.2 Kelvin. Okay. If you got this, you would have probably gotten most credit. I might have docked you like, I don't know, 0.5 points just for not seeing the values you were plugging in, if they weren't defined somewhere. But yeah, if you plugged in, let's say you plugged in 4, or maybe you plugged in 1 over 4, right? You probably would have gotten full credit for that. If you plugged in, if you may have gotten docked, a half a point for plugging in something like 4 or 2, because the reason I would have docked those points is because that pressure ratio should be less than 1, right? You're expanding from 4 to 5, so your pressure should be dropping. P5 over P4 should not be greater than 1. So yeah, I tried to give as much credit as possible, but again, might have lost a tiny bit of points. All right, so that's T5. T6 was given to us, right? Let's go ahead and try to keep the figure in there. Let's make this a little bit smaller. We'll bring that over here. All right, so state 6. I knew that guy, so T6, 600 Kelvin. State 7. All right, so we do have an isentropic efficiency for that second turbine of 0.9, so I do need to be kind of careful about that. But let's see, so I need I'm going to need state 7s, and then I'll need state 7 using the isentropic efficiency. So state 7s, I'm going to use an isentropic relationship. It's going to be T7s over T6 is P7 over P6 to the K minus 1 over K. And of course, this guy has got to be 0.5. If you plugged in, you know, I don't know, 1 over 4 or something like that, you probably would have gotten full credit at that point. Yeah. But again, if you plugged in like 2 or 4, I might have docked you a half a point or something like that just for not realizing that, oh, that pressure ratio should not be greater than 1 there. Um, all right, so T2S, or I'm sorry, T2S, T7S, 492.2. All right, but I know that I've got an isentropic efficiency of less than 1, so I do need to figure out what state 7 is. So I know isentropic efficiency of a turbine, ratio of the two works. Ideally, I get a lot of work out of it, so it's going to be the one on the bottom. So it's a Cp delta T on the bottom, T6 minus T7, Cp T6 minus T7S. All right. And so it's just a matter of solving for T7. I've got 502.98 Kelvin. If you ended up solving for just T7S and not T7, you would have gotten half credit for that particular temperature, just FYI. All right, and so at this point, I think actually, what was it that I needed to know? That's right, I've got T7, so actually at this point, I can plug things in for T3. So T3, 495.5. Yeah, so 495.5 Kelvin. Perfect. All right, and then the very last thing I needed to do was get state 8. So these guys down a little bit. That way I can have the picture in here. All right. So state 8. So you have two options here. You could have used your isentropic efficient, or not, I'm sorry, your regenerator effectiveness equation. So if you did that, your equation would be Q regen defined from this top squiggly here, which is delta H or Cp delta T. So T7 is T8 over Cp times, by the time you're working, fluid flowed from 7, right, flowed from this inlet to this outlet. It would have heated, or it would have cooled all the way off to the lowest possible temperature, and that's T2. So on the bottom, it's T7 minus T2. And you could have solved for your T8 that way. T8, 435.4. Alternatively, you could have applied an energy balance to that, to this whole thing. You would have gotten some of the m dot h's going in equals the sum of the m dot h's going out. You could have resolved that in terms of delta Cp delta T's. CP's would have canceled out, and you could have solved for your temperatures that way. So two different options should give you the exact same thing. Okay, so I try to give as much credit for those temperatures as possible if you had the correct governing equations. Yeah. So if you got penalized, kind of doubly for anything, let me know. But again, I try my best there to give everybody as much credit as I possibly could according to my rubric, right? Rubric's important for keeping things fair for everybody. So let's get our governing equations, because that was where people lost a good amount of points. So part C, asking about the thermal efficiency of the cycle. So So your thermal efficiency is 1 minus Q out over your Q in. I saw more than I want to, more than I'd like to admit, I saw lots of people define um, Q out and Q in and work out in terms of U's, right? So Q out, maybe U8 minus U1. That is absolutely, don't do that. Don't do that. Why would you do that? Um, right? You got out a thermal one. You know what an open system versus a closed system is, hopefully. Um, so your first law, let's look at it. Uh, so it's, for a for an open system, and that's what each of these devices are going to be modeled as. For an open system, dE dt equals Q dot minus W dot. It's going to boil down to, once we ignore the kinetic and potential energy changes and say it's steady state, it's going to be Q dot in minus Q dot out minus W dot out minus W dot in. And then you're going to have some things in terms of delta H's. In, out. Actually, it's out minus N. I'm sorry, out minus N. You should not see any delta U's. No delta U's, okay? And then because your delta H is equal to Cp delta T, that's where we get the Cp delta T stuff from. But if there was mention of delta U's or any U's anywhere in this system, don't be surprised if you got dot points off of that. Um, even if you eventually resolve those delta U's and you said, okay, well, it's Cp delta T. Well, that's just happening upon what it was supposed to be, but delta U is not equal to Cp delta T. That's incorrect. So you would have lost some points. So don't be surprised at that if that was the case. Okay. So with that being said, let's get our Q in and Q out. So our Q in and Q out, we've got 2 Q ins and 1 Q out. So your Q out is going to be between 8 and 1. So it's going to be a delta H or a Cp delta T. So on the top, it's going to be Cp times T8 minus T1. On the bottom, again, you've got 2 Q outs, one between, or 2 Q ins, one between 3 and 4, one between 5 and 6. So should be T4 is T3 plus T6 minus T5. Okay. Alternatively, if you wanted to put it in terms of work net out, you could have done that. Right? It's just a little bit longer. So work net out, you'd have 2 workouts, 1 work in. So on the top, have, let's see, you've got a workout for the first turbine, T4 minus T5 plus T6 minus T7. There's your workout minus your work in, which is Cp times T2 minus T1. Okay. And then your Q in is, of course, going to be the same. 4 minus T3 plus T6 minus T5. So either one of those would have been perfectly acceptable. All right. So we got that guy. Actually, I'm just going to take advantage of the fact that I know you can go back and see things. Oh, and you would have gotten, I mean, it's on the equation sheet, but you should have gotten, or the answer key, but you should have gotten 30.34%. For part D, you needed to find the net power output. So W dot net out. This is equal to M dot times little W net out. Your mass flow rate is not given to you, but you do have the volumetric flow rate. So your mass flow rate is going to be V dot 1 over your specific volume V1 times little work net out. Um, and I kind of divided it up. If you got work net out, that was half of the points, right? Maybe you defined it in part C, that would have been fine too, but your work net out should be CP, not CV, CP times uh, work for the turbines. So, come on, 4 minus 5. So T4 minus T5 plus T6 minus T7 minus the work in T2 minus T1. Here we go. Or you could have said it was equal to Q net in. That would have been okay too. I don't think many people did that, but you could have. So Q net in is anything coming in minus anything coming out. So you got things going on in between 3 and 4. So T4 minus T3 plus between 5 and 6. So T6 minus T5 minus the Q out, which is going out between 8 and 1. So T8 minus T1. Either of those would have been perfectly fine. And then this guy right here, I'm going to erase this guy right here, but this was worth 7.5 points if you got that. The other 7.5 points of part D was this guy right here. So V dot 1 over V1, and then you do need to put that V1 in terms of R T1 over P. And some people said that wrote maybe like a PV over RT or something like that. Make sure that you put a dot, number one, so that I know it's mass flow rate, volumetric flow rate. Also, you would need to indicate that it's at state 1, and you would need to actually plug in those, show me what is this R, what temperature are you using, right? So if you didn't do that, you wouldn't have gotten full credit, but I would have tried to get you some points, right? So this is going to be 7 meters cubed per, oops, not kilogram, but 7 meters cubed per second over your R value. For air, it's 0.287 kilojoules per kilogram K times our temperature at 280 Kelvin. And then your pressure, it's 1 bar. If you put it in terms of kilopascals, your units are going to work out because let's see, 1 kilopascal is a kilonewton per meter squared, and a kilonewton meter is a kilojoule, and that should make your units work out correctly, right? Kilojoule, kilojoule, Kelvin, Kelvin, kilopascal, kilopascal, kilonewton, kilonewton. Yeah, and you should be left with, remember this whole thing is your m dot. And so you should be left with units of kilograms per, this guy, those meters. You should be left with kilograms per second. So I've got 8.71 kilograms per second. Yeah. And so when you plug everything in, you should have gotten you should have gotten 498.2. So 498.2 kilowatts. All right. So again, try to give you as many points as possible. Please go through the rubric that's posted online and grade yourself. And if you don't think that that your grade reflects what you should have gotten according to the rubric, let me know. Keep in mind, I'm applying that rubric. That was applied to everybody. I try to make it as fair as possible. So do be aware that this is my effort of being transparent of where your grade is coming from and give you a little bit more room to argue back for points in a fair, consistent manner. So, all right, let me know if you have any questions, and yep, see you in class. Thank you.